Hello and welcome to this video tutorial on using the higher order the implementation of the higher orders of anisotropy in vampire. So these higher order terms, they're quite useful when simulating permanent magnets because, well, they have interesting temperature dependent properties, which hopefully we aim to simulate. So just to start off with, we start with the Landau-Lifshitz-Gilbert equation. We have a spin precessing in some effective field, and this effective field can be derived by taking the derivative of the Hamiltonian with respect to the spin, and we can also add in a thermal field to add the temperature effects. So in our Hamiltonian, we have lots of different contributions, and here we're going to focus on the anisotropy contribution. So here, the standard form that anisotropy is usually written in, we have just different orders of sine squared theta. But in permanent magnets, we can also have rotational terms. For example, this one here, which depends on cos 4 phi. So the phi is the angle measured from the x-axis in the spherical polar formalism. And this is all because of the symmetry of the sites where the atoms are situated in the crystal. And here we have an example of a permanent magnet of neodymium iron boride, and the symmetries of the sites will all depend on the space group P42/M in this case. We'll go into more detail into that later. So here's an example of how these anisotropy terms might manifest themselves. So this is some experimental data, ramping up a single crystal of neodymium iron boride. And we have here that when we ramp the field in the 100 direction, there's a big jerk or sudden increase in the magnetization. And we see this because the spin directions are trapped in essentially a local minimum in the energy, and as the field ramps up, eventually it overcomes this minimum and moves into another one quite quickly. So we see this big shift. So the way we represent these terms in vampire is via the real spherical harmonic or tesseract harmonic terms. We choose these because it's an orthogonal expansion, and the Callan-Callan law scaling works for the orthogonal function. So if we get the L value of the harmonic and plug it in, we know that the bulk anisotropy will depend on this L plus 1 over 2 power law shown below. So as we can see here, the higher orders of anisotropy have decreased more quickly. And have effectively disappeared. So now at 275 Kelvin, this first order magnetic process is no longer shown. It no longer manifests itself because the higher orders of anisotropy have essentially disappeared and there's no more of this local minimum occurring. So in the case of neodymium iron boride, the neodymium atoms are situated at the 4F and 4G sites of P42M and M. And so these sites all have a point symmetry of m dot 2m. So the m refers to reflection in the plane perpendicular to the c-axis, and then the 2m indicates two-order rotational symmetry and also reflection symmetry in the plane divided by the c-axis and the 110 axis. And this restricts our allowed terms as shown below. So we only have even and positive powers of n and even positive powers of L. And it's quite simple to transfer between the formalism. It's usually a case of starting at the higher orders and working your way down. So here's an example which can be found in more detail in Ralph Skomsky's book. And here's to show we did some uh, simulations to check the temperature dependence. And we see that for the L equals 4 um, rotational term, we get the expected order 10 dependence on the bulk anisotropy. Okay, so on implementing this in Vampire, so if we go back to the um, previous slide first, we want to take we want to select the 110 direction shown here as the x-axis. But first, just to indicate something, so one of the first things we have to do is when we're in the vampire directory, you should type in this command because it's not fully implemented yet. Soon, once it's gone through more testing, we'd be happy to put it into develop. But at the moment, it's in the magnetocrystalline anisotropy branch of vampire. So in your vampire directory, just type in this command just to put it to the correct version. Now, if we want to set our x-axis, we can get we do all this in the material file. So if I cd material file here, we can. So this is some information for a neodymium ion boride simulation. If I want to add in these anisotropies, the first thing I should do would be to set the x-axis to the 110 direction. So automatically it's set to the 100 direction. If I set it to the 11, and I can set it to the 110 direction by using this command, the rotational anisotropy direction. Furthermore, I want to add in, say, well, one way to add in the second order uniaxial anisotropy would be to use this command, second order uniaxial anisotropy constant, but this is equivalent to writing also 2 0 order anisotropy constant and whatever you want there, and then we can go through the others with the first number indicating the L number of the harmonic and the second the M number. So 2-2 would be Y22. We can do this. So we have implementation for at the moment for just 2 0, 2 2, 4 0, 4 2, 4 4. So all these even up to 6 6. And more details can also be found in the paper at the bottom here. But in any case, that should hopefully give you enough information on how to use this implementation. And thank you very much for listening. I hope that helped.